All right. Hello, everyone. Good afternoon, good morning for some of you, good evening for some of you. Welcome to this webinar on the hot topic of N2O emissions. It is a topic we are all very interested in as a wastewater community, and it is gaining significant importance. And today we have the pleasure presenting you content that relates to the root causes of N2O emissions in wastewater treatment bioreactors, and also what to do about it once you know those root causes. So thanks for joining, all of you. We have really many people from all over the world joining. Actually, 271 people signed up for this webinar today. So we are truly excited to having you all in this webinar. So what are the objectives of today and what is the format of this webinar? Well, of course, I already said it. N2O is a very important topic. It was not like that maybe a decade ago, but nowadays the importance is growing a lot, or at least the attention, because as wastewater community, we realize that the contribution of nitrous oxide emissions to the global carbon footprint of the water industry is significant. And we hope to achieve two things today, maybe a couple of more, but these are the key things. So we want to provide you with new detailed process insights that have really practical value for you, things you can use in your daily operations, and also that you understand the practical application and the potential of CFD combined with kinetics of N2O for assessment of N2O, but also to test mitigation strategies. So the format is a hybrid mode. We will do some mixture of slides and live questions and answers. And then also there will be intermediate polls. So you will have the ability to also vote and give some answers to some open questions we will ask. So if you have questions, which we would actually highly recommend you to ask, we would recommend you to use the Q&A button. So if you hover over your screen, you see a Q&A button. Please use that for the questions, not the chat, okay? And we have a team continuously monitoring the Q&A and the interesting questions or questions that are very relevant to the content at hand. We will bring live and answer live. There will be a short questionnaire after this webinar. Please fill it in because we highly value feedback and we want to continuously improve. And of course, we also want to make our webinars for the future even more relevant. So what do we have on the menu today? Well, we decided to provide you with quite a dense webinar. This means there will be a lot of content. You will have to be sharp, but we also think we have to value your time a bit. And yeah, why not stack it with full of content and provide you with most of the insights in this coming hour. But of course, we will not only talk, we also have space for questions and answers. So the first part is an introduction and a short recap of the previous webinar. We already did one webinar on N2O, which had completely different content. And we would recommend you to watch it if you have not done so already. Then we go to the meaty part of this webinar, the root causes of N2O production and how do you use them to develop tailored mitigation strategies. We end with the conclusions of this webinar. Okay, so maybe it's interesting to start with who we are. That's always good, who we are. Why do we set up this webinar? Who is AM Team? We will not spend too much time on this, but we are a company based in Belgium, and our mission is to challenge the status quo in process engineering for optimal use of resources. Resources can indeed be energy and chemicals or different types of resources we want to save in the water industry, but we also look at it very widely. It can also be a measurement campaign to keep it as lean and short as possible. And also, if we look at the biggest resource we have, our planet, the N2O piece, the N2O question is a very relevant one. So this is how we look at resources. We are a company headquartered in Belgium, but we work with customers all over the world, and we are happy to work with a lot of them on this slide. And they are the three categories we all know. We have the end users, which are the water utilities, both at the drinking water side and the wastewater side. Then we also have a lot of technology companies we work with. And then we also work and partner with engineering and consulting firms. So we help all of these people accelerating process, scale up, design, development, optimization, and also we enable them to have smart operation. So we really want to digitally enable our customers with very good process models. So this is the theme of today. I'm already talking, so let's start with me. I'm Wim Oudenaert. I'm CEO and co-founder at the M-Team, and it's my pleasure to be presenting together with my colleague, Roberta Muyo. She is project manager and simulation engineer at the M-Team. And then we also have Giacomo Bellandi. He is also in this call. He will be taking a lot of the questions, senior simulation engineer and highly specialized in N2O, actually. We also have Dr. Usman Rehman. He's my fellow co-founder and our CTO of the company. And then we also have Anna Sofijanic. She could not be in this call because currently she's traveling in Denmark and Sweden to visit customers and utilities. And many of them are actually joining in this webinar as well. So good to have you here. Anna helped setting up the webinar. So let's start with the content. On the first part, the introduction and the recap of the previous webinar. Well, the context is big. N2O has a carbon change or a footprint potential of 300 times that of CO2. So many people have seen this number. So actually, you don't have to emit a lot to have a big impact. And this, of course, leads to some key numbers. If you can look at this sentence here, actually, N2O can increase the carbon footprint of a wastewater treatment plant with up to 80%. It's only that gas. And if you consider that we, as a water industry, are responsible for more or less 3% of the global emissions, N2O has approximately 26% of that. It's ballpark numbers, but it's really a big percentage of contribution. Yeah, and where is it formed? Mainly in the aerobic and anoxic tanks in the biology. That's what you can see here. And this is where we are going to zoom in on in this webinar. Multiple countries worldwide start focusing on it heavily. And actually every year this list is growing. And now we see a drastic increase of attention of this topic. So last webinar, we asked the questions, what are the major difficulties practitioners face? And actually, you can divide them in two categories. The first one is the assessment. How good or how bad are we doing? Typical questions that pop up there are, how is the N2O emission at my plants? Which ones are the hotspots? How do I prioritize? And how do I adequately assess those emissions? And then you have the second stage. Of course, once you have a view on that, you want to mitigate. So you want to reduce your carbon footprint. But there are other important questions. For example, what are potential mitigation strategies? Which ones will be most effective at my plants? And what is very important is if we look at the key topic of wastewater treatment, it is treating wastewater. So you don't want to compromise your effluent quality. And last, and that's also a topic we will try to touch upon in this webinar, what are the generic learnings every utility or every plant can potentially apply? So we really have to search for them. So again, if you're interested, you can go to our website, amteam.com/N2O, and you can find also on our YouTube channel, the full recording of the first webinar. Another slide from the last webinar is what drives N2O emissions. So on the one hand, we have influent quality. We should not explain that what changes as a quantity and a quality is important. You have to adapt your operation to that. Also, operational changes can be made, and they can be very specific for plants. And then, of course, you have a huge variety of systems. We don't only have conventional activated sludge, for example, but even within one category, you have a tremendous amount of different designs. So that's the reactor type and the design. And a very important topic we wanted to highlight is also the local conditions. And actually, this is very visible if you combine CFD, which is actually a 3D simulation, with biokinetics. So what we see on the screen right now is a bioreactor, a top view and a side view. And if you do some simulations, you can visualize gradients of local oxygen, local ammonia, local N2O, local nitrites, and things like that. So this is possible with this combined framework. Typically, when we look at full-scale systems, you see very drastic gradients, not only in the length, but also in the width and the depth. Just look where this gas hood is measuring. Well, you can already imagine that if you would move it a few meters, or you are measuring liquid N2O, and you would move your sensor with 5 or 6 meters, that it would have an impact on how you take conclusions and how you calculate your emissions. This topic has been an important topic in the previous webinar, so feel free to watch it back, but that's definitely something that is important. And next to mitigation, we also support these measurement campaigns very well with this tool. Okay, so that was a short intro, setting the scene a bit. And now we go to the meat of this webinar. So we decided to go rather deep in the mechanisms of N2O because we think it is very interesting to understand them, because we think you also can take better decisions based on them. But we try to also make it digestible for people also that have not too much of a background of N2O. We took that risk, but don't misunderstand us in this webinar. So we will go deep, but in fact, the practical outcomes, and that's what we try to illustrate in the last part, are actually there. Yeah. So the root causes of N2O production. When we look at the basics of wastewater treatments, I think most of you know nitrification, denitrification. That is really the core of nitrogen removal. So you have two bacteria, the autotrophs and the heterotrophs, that are collaborating. It is the same in a conventional system or a biofilm system. The configurations are different, but they are collaborating. So the first group, the autotrophs, they actually oxidize your ammonia and they add some oxygen more and more until nitrates. This is nitrification. And in the end, then if you feed this to heterotrophs, which actually eat carbon as a source, they are more comparable to humans. They eat organic carbon. The autotrophs don't really eat organic carbon. That's why there is nitrogen here. Yeah. So these people or these bacteria bring them back to nitrogen gas. And this is, of course, not a greenhouse gas, but in the process of it, you have a side step or you have an intermediate, which is called nitrous oxide. So this is a first take home. The heterotrophs have one pathway of N2O formation, which is in fact part of their core business. So if you want to denitrify, you always have to go over nitrous oxide. So it's not per se bad. It's only bad if these heterotrophs cannot consume this in order to turn it into N2 in a later stage. Yeah. So then we go to the autotrophs, and unfortunately, they work not really in a straight line. So these bacteria have a side track here, and it depends on the local conditions. Typically at very high dissolved oxygen, high ammonia, they can actually form N2O from this intermediate, which is called hydroxylamine. Yeah, that's one pathway. And unfortunately, they also have a second one from nitrites. They can also form nitrous oxide. And this happens under different conditions. This time, low DO, high ammonia. Okay, so that's kind of the summary of this mechanism. So if we summarize it in 3 lines, while autotrophs can produce N2O in 2 ways, the heterotrophs can actually produce N2O in 1 way. But important, very important, is they can also consume N2O in 1 way. So the net balance might be even negative or neutral. Okay, so that's the summary of them. And to make it easily digestible for you, we will refer back to these blue ones, the autotrophs, and we will refer to them as A1, A2, and we will also refer to the heterotrophic pathway as H, the brown symbol, okay? So if you see these symbols reappearing, these are the 3 pathways of N2O formation. Good. So let's go to a case example. We will give the floor to Roberta Mbuyo, and she will be introducing a real case example. Roberta, the floor is yours.
Yeah, thanks, Wim. So here we are presenting a pilot scale reactor, which is currently used by the water utility Watercare in New Zealand to investigate the N2O emissions under different operating conditions. They are doing some measurement under different, for example, influent conditions to evaluate the N2O emission. We are collaborating with them within a project, and the goal of the project is in fact to enhance piloting an on-site measurement campaign to enhance process understanding about N2O and biokinetic ASM in general, and to obtain an effective mitigation of greenhouse gases. So here we see it's a conventional system that Wim already mentioned earlier. So it's a denitrification zone followed by a nitrification zone. In the first part of the reactor, is anoxic. So we see an inlet, influent wastewater, and secondary settler recycle stream. This both enters the system, and in this zone we have higher DOC, higher COD, higher ammonia, and then denitrification occurs. Then the flow passes through this window that you can see on the bottom, and it goes to the aerated zone. In the aerated zone, the ammonia nitrification occurs, and also the COD oxidation. So basically, in this zone, you have higher dissolved oxygen concentration, lower COD, and lower ammonia. So this is what we would measure. So in this slide, you can see the liquid N2O concentration and the gas N2O concentration. This is a 3D CFD simulation, what we call a volume rendering. So a 3D visualization of, in this case, a concentration of a certain variable N2O inside the reactor. So on the left, we see the dissolved liquid N2O concentration, and we can see that higher concentration in the anoxic zone and lower concentration in the aerobic zone. In fact, red means, it's a magnitude of concentration. So red means high concentration and blue means lower concentration. And we can also see in the gas that the higher concentration, the higher gas concentration are in the top part of the reactor and in the central zone where the plumes get out of the system. So this is exactly what we would measure in measurement campaign, placing some sensors.
Thanks, Roberta, for introducing this case. We will come back to this case later because this was not really the root cause. But what we would like to touch upon is the three-step process. So what Roberta has shown is actually the result of this three-step process. So the first step is N2O, nitrous oxide, gets produced somewhere in your bioreactor. I already explained how. So there are three main pathways, either by these bacteria or either via the two pathways of the autotrophs, okay? Just imagine they would not produce any N2O, we would not have an N2O issue. So that's really the root cause, is these three pathways. So what happens secondly is, even though N2O is a gas, it is actually starting in the dissolved form. So it gets transported through the water flow of your system, and that makes it hard to, of course, know the root cause because it's already going away from that. And you will measure it somewhere in the form of liquid N2O. And in a third step, and this is really causing the emissions, your N2O gets emitted because it gets stripped due to the aeration. So the liquid N2O joins the aeration bubbles, the air bubbles, and goes up, and this is really causing the emissions. So what we really measure is typically with liquid sensors or gas measurements, the N2O in the water phase or the gas phase. But really the root cause is here. And what is also important is what gets emitted is causing the climate impact. So we have to distinguish between what we can measure, what causes the climate impact, and what is the root cause of the problem. So if you approach this from an engineering point of view, we have actually two choices. So either we address the root cause, which means avoiding N2O to get produced or lowering the production of it, or we treat the gas, and that's an end-of-pipe solution. For some reactors, it works because they are covered. And then you also avoid the environmental impact. But of course, in this webinar, we will be focusing on step number one, which is really the root cause. And we believe if you understand the root cause, you can really effectively mitigate. So Roberta, back to you.
Yeah, thanks, Wim. So back to the pilot reactor. Here again, we see the dissolved N2O concentration in the liquid, in the anoxic and the aerobic zone. What is interesting to see is that the concentration is quite homogeneous in the reactor. So it's concentration, higher concentration in the anoxic zone and slightly lower concentration in the aerobic zone. So actually here we are measuring, actually, if we put some sensors, we are measuring the symptoms, but we don't know where is exactly N2O originating from and why is it produced. So then if we go a step back in step one that Wim mentioned, what we would see is, what we would focus on are the root causes. So here we are looking at the production rate, so the speed of reaction of heterotroph in this case, so how fast heterotroph produce N2O, the kilograms cubic meters per day that is produced by heterotroph. And here we are looking at 2D images. It's a side view of our system. Here, what we are seeing is that heterotroph produce N2O of course, in the anoxic zone, which is expected. Now, if we go to the heterotroph pathways, A1 and A2, what we see is that A1 occurs in this transition zone between anoxic to aerobic, where you have lower oxygen, but also high ammonia availability, and kind of the same for A2 processes. Now, if we would finally quantify the root causes, we would see that in this case, 57% of the N2O is produced by the heterotroph and the remaining fraction by the autotroph. So it's interesting to note here that despite the two pathways of autotroph, A1 and A2, occurs mainly in this transition zone, they account for almost 50% of the N2O production. Now, we can do a simulation, a scenario where, for example, we simulate what happens if our ammonia load increases. It's very common, it's ammonia increase during the day in our influent wastewater. So basically what we see is that the heterotroph produce slightly less N2O. But very interesting to note is that now the autotroph produce much more N2O than the case before. So in the end, what if we again compare and quantify the root causes, we would see that actually in this case, the autotroph produce much more. Wim, if you go to the next, please. Yeah. Here, if we would compare the two scenarios, we would see that with high ammonia, the autotroph pathways are much more important in the N2O production. And in particular, the A1 process accounts for 63% production. While in the low ammonia scenario, most of the N2O was produced by the heterotroph. So as you can see, a change in the influent composition or even a change in the operating condition we will see later can drastically change the picture, can drastically change the way N2O gets produced. And going to step 3, so really quantifying the emissions, here we're looking at the N2O gas emission rate. So how much N2O it gets stripped in the off gas. And again, we are comparing the low ammonia scenario and the high ammonia scenario. So what we see is that basically by increasing the ammonia load, the N2O emission increase by a factor of 50%. So as you can imagine, it's a huge variation that can happen on a daily basis in a wastewater treatment plant. And this is exactly what Explicit also measured by their drones. So Explicit used these drones to basically map the gas and it are able to measure the N2O emissions in the gas phase. So if you look at the plot here on the right, you can see that basically within 2 hours, they could measure, they could observe a very wide fluctuation of N2O emission between 50 and 100% difference. And this can be caused, for example, by a change in the influent organic concentration, influent ammonia concentration. So going back to the pilot reactor, here we see the summary of the N2O concentration in the gas and in the liquid in the two scenarios, low ammonia scenario and high ammonia scenario. So this is what we would measure, placing some sensor or hood in for measuring the off gas. So basically what we would measure is an increase of N2O in both liquid and gas in the case of higher ammonia. Finally, we can quantify the final goal is to really quantify the emission in terms of CO2 equivalent. So here we are proposing two indicators. Here on the left, the yearly emission CO2 equivalent emission, and on the right, the emission factor. So how much N2O gets emitted per ammonia influent load. So basically what we can see is that by increasing the ammonia influent concentration, our yearly emissions more than double. While on the other side, we can see that the emission factor is slightly reduced because it's also linked to the influent ammonia, which increase. So basically, this is just an interesting point to mention that emission factor should always be accompanied by some other indicator, for example, the yearly emission in this case.
Okay, so thanks, Roberta. So we will go to full-scale plants in the next section, but this was like an introduction because it's a simple to understand system, just an anoxic zone and an aerobic zone. And Roberta has shown actually that our model brings these three steps nicely together. So the first one is the production. We have, of course, the kinetics inside the model. So these kinetics tell us where it gets produced at which rate, so which mass per second or per hour of N2O. Then we have the production, of course, and then we have finally the stripping with the gas, causing the final emissions. So if you paid close attention, what you measure is actually a consequence of the first step, but the gradients of the local hotspots of production are quite different when you compare to the gradients you would measure on site. And that makes it very hard to interpret such systems or to know the root cause. So we have explained that the root cause can be found in three mechanisms, three production pathways. And also if you change a bit of the conditions, not only the influent, but also the operational conditions or a design, these pathways can react very, very differently. It all depends on the local conditions of dissolved oxygen, ammonia, and carbon. So on-site N2O measurements, either gas or liquids, they reveal the symptoms, but actually we believe that in order to cure the patients, it really lies in addressing the root causes. Okay, so that was the first intro session on the emissions of N2O. I will go to my colleague Usman and will ask if there are any questions.
Yes, thank you, Wim. There are a couple of questions. One question is it possible to separately measure or strategically put sensors to measure A1 and A2 process, for example?
So maybe Giacomo, are you able to answer this question?
Yeah, thanks for the question. So distinguish with a single measurement between the two pathways, it's tricky. And actually the three pathways might occur at the same time. Actually, you have the production and consumption by the heterotrophs and then the productions from AOBs. So with a single sensor, it might not be feasible. But you can assist that with the current knowledge and the use of the models.
Yeah, the problem is a bit, they are not like reactive tracers, huh? N2O 1, 2, 3. We don't know where they come from. Yeah, indeed. Other questions, Usman?
There are more questions, but I know you will be answering them later in the, so I will let you continue. Yeah.
We will come, okay, perfect. We will come back to that. So let's go to the mitigation strategies, and we talk about tailored mitigation strategies because tailored has to do with the specificity of a certain plant or a site. And Roberta will be introducing a full-scale case. And then also we will be showing some pure oxygen measures. That's more a design measure, let's say, or other measures, for example, increasing a sludge concentration. So these are all examples of potential mitigation strategies, and they are kind of summarized in this figure. So either it's on the influence, for example, if you can adapt a feeding strategy. Of course, it's not always easy with existing plants, but for example, we have step feed plants where you introduce the influent differently, and that has definitely an impact on the N2O emissions. Then you have operational measures, for example, adjusting an aeration, which is a very popular and well-known measure. Then you have, of course, design/reactor type changes. For example, changing a mixer or changing an aeration system or adjusting that. And of course, these three together are causing an interplay of gradients and mixing. So that's all very important. So we can play with these things together, but it should be a bit tailored to the plant. And this is what we are going to illustrate a bit in this section. In a nutshell, it comes down to avoiding extreme conditions in transition zones. For example, moderate DO level instead of a very low or a very high one. That's dissolved oxygen. Optimal sludge retention time, optimal COD, so the carbon nitrogen ratios, adequate mixing in the denitrification and nitrification zones to maybe limit and minimize these transition zone volumes. So these are all measures that can be taken. But of course, one of the biggest questions our industry right now has, what are the best mitigation measures? Which ones would work? So with one case example here from Canada, Roberta will give some further explanation on oxygen.
Yeah, so here we're going to see a full-scale bioreactor. This bioreactor is from a wastewater treatment plant operated by a utility in Canada. Here you see that anoxic, anaerobic, and oxide zone, followed by fine bubble aeration. There you see where the influent pipe is located. You also have internal recirculation for NO3 recirculation, sludge recirculation, and your outlet pipe. So basically, we are doing this project together with this Canadian utility because their ultimate goal is to reduce their carbon footprint, so the greenhouse gas emission from operation to support their climate change mitigation strategy. And we are currently collaborating, and we are using the CFD N2O model to inform upcoming fieldwork to help them and support them in the next measurement campaign. So in this plant here in Canada is as a very big challenge with seasonal variation, because in winter temperature can go down. It can vary between -10 and -20 Celsius degrees. So it's a huge temperature difference that can occur along throughout the year. This is, for example, in this slide, we are looking at some N2O emission from two wastewater treatment plants in the Netherlands, operated by the wastewater utility Eindmaas, which kindly provided this graph. So basically, in the left graph, you can see that there is a clear pattern, a clear decrease of N2O emission during the summer, while in the second plan this pattern is no longer that obvious. So basically, it's N2O emission seems to be correlated with temperature, with seasonal impact, and higher emission can occur in winter, but it cannot not be the same case for all the plants. So it's very case specific, and we're going to start a project with this utility to really investigate these issues further. So going back to the Canadian plant, here we see the root causes. So here first of all, we look at the heterotroph production rate, and we're looking at two different scenarios. One is at 11 degrees, and the other one is at 20 Celsius degrees. So two different temperatures. First of all, the first thing that we can notice is that at 11 degrees, the production of heterotroph reduced. So basically, they slow down their activity. But actually, it's also important to mention that the production reduced, but also their consumption reduced. This is very important to highlight here. And then if we go to the autotroph pathways, we can see, starting from the temperature at 11 degrees, we can see that the A1 process, the production kind of squeeze in between the anoxic and aerated zone. So the transition zone between anoxic and aerobic is gets reduced. But on the other side, we can see that there is some production by the A1 process in the final part of the reactor, where the N2O concentration are quite low. For the A2 process, we can see that the highest production is now reduced at 11 degrees, but their production is occurring throughout the whole aerated zone. So basically here, if we go and quantify the root causes, we would see that in this case, 70% of the N2O emission at 11 degrees are 72% is produced by the A1 process, and the remaining by the A2 process. Similar for 20 degrees. So what is very important here to see is that actually heterotroph in this case, they don't produce basically any N2O. And the reason is that they produce what they consume, what they are producing. And they are even consuming more than they are producing. So if we quantify the emission, we can see that in the end, at lower temperature, so at 11 degrees, the yearly emission and also the emission factor increases. Now we go to a mitigation strategy. So it's a common knowledge that reducing your aeration is an effective measure to reduce also the N2O emissions. So we are still in the Canadian plant, and here we compare a scenario with average aeration, and we see the N2O concentration in the liquid and in the gas. What we can see is that concentration increases in the anoxic zone, concentration in the liquid increases in the anoxic zone, and then what we can see is basically in comparing the two scenarios is that by reducing the aeration by 20%, actually our concentration in the liquid and in the gas increases. So this is the very first results. And why is that? It's because by reducing your aeration, you are also stripping less, which means that your N2O in the liquid gets accumulated, and therefore also your gas gets more concentrated. If we go a step further and we look at the root causes, again, we start with the heterotroph production, and we can see that with lower aeration, there is a bit more production of N2O, but actually there is also a higher consumption. So in the end, the net production by heterotroph is even negative. If we go to the other pathways, so the autotroph pathways, here we see that with lower aeration, the transition zone between anoxic to aerobic increases. So we can see that there is more production by the A1 process. And same happens also for the A2 process, because our ammonia lives a bit longer in the system, and then therefore you end up with enhancing this pathway. So again, quantifying the root causes, what we see is that in case of 20% less aeration, it's basically half and a half. So all the N2O is produced by the autotroph, and it's spread equally between the two pathways. With average aeration, we have slightly more production with the A1 process. Quantifying the emission, so it's from this graph, it is clear that reducing your aeration is an effective measure to reduce the emission, the CO2 equivalent emission, and also the emission factor is lower. However, it is also important to highlight here that it is an effective mitigation strategy. However, we could see some side negative effect. For example, the autotroph pathways increase their formation. So it's important to mention that there are there is a need to fine-tune, to refine the mitigation strategy to counteract this side effect, for example, by controlling the aeration packages specifically.
Okay, so I suppose there must be a lot of questions because a lot of things pass by. So Usman.
Yes, there are a lot of questions, but I will, of course, go a bit strategic. So one question maybe you can respond to is because you showed the graphs between in summer and winter for these two touch blondes, and could it be that these changes in N2O could be not because of temperature, but could be ammonia loads or some other factors, seasonal factors?
Yeah, in this case, Usman, indeed, we have actually the people of the water board, water authority here attending. They have done quite some thinking on this, and it's not that easy actually to unravel the root cause, like what is causing this. And so, yeah, it's always a combination of looking at the influence, of course, temperature, operational changes, but so far the answer is quite unclear.
Yeah, that's a bit of a struggle when you come and look at the real scale plot, and if you have to like really one by one distinguish between all the different factors which are combining or contributing towards N2O. With the model, this is possible because you can actually see one by one which affects to what extent, and that's how you can kind of quantify the contribution from different factors.
Mm-hmm.
Okay, do you have time for another question or?
Yes,
later?
Go ahead, Usman.
Okay.
Put it back.
Is it possible that heterotrophic anoxic production of N2O can happen in the aerobic zone?
Giacomo, this is a question for you.
Okay, yeah, thanks. Yeah, indeed, this can happen, especially at the beginning of the aerobic zone, when we have streams entering the first aerated compartment of the aerobic zone. You can have a transition zone with volumes that are still anoxic. It's not black or white, right? Their activity will switch to the aerobic in like gradually, and this will cause the intercurrents of different pathways at the same time, and we see it in yeah, more or less every plant.
Okay, so yeah, Usman, we will come back to the Q&A. Yeah, is it okay if we go a bit further now?
Yes, perfect.
Okay, perfect. So we focus now on one mitigation measure, which is adjusting your aeration. But there are, of course, other ones that are actually quite proven. For example, this is a slide from Dr. Mikkel Andersen. He's the CTO of Unisense, and he presented this slide at the World Water Congress not so long ago. And what they did in one specific case is increased MLSS levels, so the sludge levels. This is the green scenarios. And they compare them with the cases with lower MLSS, just the regular, which is the blue and the red line. And in that case, because of the specific load, yeah, it's because your mass of the biomass goes up and your specific loading goes down, they could actually reduce the N2O emissions quite significantly. So again, it can be plant specific. In this specific case, this worked and was quite proven as a mitigation measure. But other measures are, for example, working more at a retrofit or a change, more drastic change of your system. One of the examples is an aeration system. For example, you could investigate what if we go for a hybrid aeration. For example, what if we complement an existing bubble or a surface aeration system with a pure oxygen system? And this is a project we are currently working on together with industrial customers with Air Liquide. And yeah, this allows to nicely compare these scenarios and look at also the stripping impact, because in this case, stripping leads, of course, to more or less N2O emissions, but it also has an impact on the kinetics. So again, doing these simulations, we can unravel really what happens in different scenarios. So without going into too much detail, because this project is still ongoing, I just wanted to show you a couple of plots of local oxygen and nitrites. Okay, so these variables are also in 3D available. So what is the key point of this section? That ideally your mitigation strategies are linked to the root causes. And actually, if you start thinking about it, for example, Roberta highlighted that you can lower your aeration, but you can also refine that, because aeration in that specific plant had also an unwanted side effect. The autotrophic production went up. What if you further refine your aeration to also knock down the production by the autotrophs? It would lead to even more mitigation. So the possibilities are really wide. And yeah, we have to understand some strategies. Not a single strategy will be perfect. Every strategy will have some undesired side effects. So typically the 4 categories of mitigation are influent, operation, system design, and mixing. So this is how you can actually, these are the handles you have as an operator to play with that, but of course, without compromising the effluent quality. And what we really hope is that there are some guidelines that are plant generic or utility generic that everybody can kind of use to some degree. And of course, some of the measures will be very plant specific. Okay, so then how do we apply this now, this model in a further way? Well, the first phase, and many of the utilities right now today are in this stage, they are either planning to start measuring N2O, or they are starting to measure N2O. Well, the first phase is this assessment. So is the hotspot analysis. So in those cases, we actually run the model alongside measurement campaigns to enhance data, to also guide measurement locations, and then to also do a general quantification of the emissions. In such cases, typically the first results are available in just 2 or 4 weeks. I just wanted to highlight that because I know it looks sophisticated and it might look complex, but in the end, it's a very practical engineering tool. How does it work? What do we really do on advising measurement campaigns? It is about the resolution of measurements. For example, how many sensors would you use in that specific plant, or are you using hoods or not? Can we optimize that? Can we maybe also look at the duration of your measurements? And what is very important, at the location of the measurements. Because in this plug flow reactor, you see a rainbow pattern, which is always the case in a plug flow system. It's kind of a gradual change along the length. But in many, many systems, we have seen gradients along the depth, but also along the width. So you have to be a bit careful with measurement location. And then, of course, we add context to data. For example, if you try to correlate a nitrate measurement to an N2O measurement, but this nitrate sensor is located 20 meters or 50 meters downstream or upstream, that is quite a, you have to have some context there to make sense out of it. So this is what we do in phase 1. Phase 2, typically we do virtual process redesign. So we literally test mitigation strategies. For example, what if you would lower your aeration, or can we further refine it? Winter versus summer, should we do things differently? Things like that. And in a final stage, we go for the on-site implementation using models or using measures on-site to really mitigate without compromising effluent quality. And again, typically we look at effluent quality together with N2O, because you can optimize both if you do such a study. Again, this is not a one-man show. Typically, we work with a lot of partners locally that have complementary skills in the areas to provide even better and more complete solutions. Okay. What is also important is some of you might be working with different systems than conventional activated sludge. For example, biofilm, granular sludge, trickling filters, shortcut nitrogen processes. We are working on those things as well. We just wanted to highlight that we want to broaden the application to those specific, sometimes highly loaded systems. And then also other developments are the partnerships we are setting up. For example, we have set up a partnership recently with Binny's for the UK, Singapore, and Hong Kong markets for really offering more complete solutions in those markets. Binny's is a consulting and engineering firm. And also we are very open to strengthen collaborations with other parties that have complementary skills. This brings us a bit to the conclusion. And of course, after the conclusion, we have residual time to answer more questions for this webinar. So conclusions of this webinar, we believe that the on-site measurements are valuable, of course, because they show you an extent of a problem. They reveal the symptoms, but so they see if you are a bit of sick, or it's like a thermometer you use to measure the fever, let's say, right? And it's not always that bad, but curing the patient really lies in addressing these root causes. And ideally, your strategies, your mitigation strategies are linked to these root causes, and the possibilities is, if you start reasoning from that perspective, are quite wide to reduce emissions significantly without compromising effluent quality. Most of the strategies will also have undesired side effects. So you really have to take these into account. You don't want to lose your effluent quality or have higher operational costs, for example, or some potential other ones. So you have to understand those. And the combined tool, so the CFD N2O framework, really reveals those root causes and allows the what-if testing for mitigation. And that's quite powerful because you can do a lot of scenarios before you do any change on site. And then again, we support measurement campaigns to test those changes. So that's the conclusions of this webinar. So for the people that really have to leave and have to go to another meeting, we want to thank you very much for attending. It was a great honor having you here with so many. We hope it was interesting. And please fill in the questionnaire because we value feedback a lot. So we hope to see you again. And for the people, the real diehards, let's say, that will still want to continue, we of course can continue with some residual Q&A. Okay, Usman, back to you.
Yeah, thank you, Wim. Maybe some hot question which has came for like 4 or 5 times is by reducing the aeration, do you look at the effluent quality? And there's also a question about how you can, instead of linking your N2O with the N2O emissions with the ammonia load, but can you not connect it with the ammonia removed? Because that might be an even better factor.
So yeah, Usman, you did quite some work on that in the past. I'm looking at you. Can you answer it?
Yeah, so I think in the specific case of the pilot, where we had a 20% reduction in the aeration, of course we looked at the effluent quality, and effluent quality in this case was still within the limits. But that's actually one benefit of using such a tool, because it not only looks at the N2O, which of course is the main driver for causing the mitigation strategies, but there are a couple of other things that you don't want to deteriorate is your effluent quality. But I think this model or this tool certainly helps to make sure to choose the mitigation strategy which allows you to have the similar or not, let's say, the worse effluent quality than the current design, for example.
Yeah, exactly, Usman. I can add to that. For example, if you look at the Netherlands, that's a specific case. In some regions, you have high population growth. In others, population is decreasing. So there are shifts happening. Many wastewater treatment plants have varying loads, and they are facing changes for the future, combined with way more stringent effluent limits in 2027 by the European framework. So it's very hard to just mitigate N2O in that case without looking at how do we even improve our effluent quality, not just maintain it. And secondly, how do we avoid maybe having to build an additional bioreactor in the short term? Maybe we can make optimal use of our existing infrastructure. And in those projects, N2O is just one of the goals of the project. Yeah.
Okay. Yeah, there was a question also about pure oxygen. So the graphs you showed were about nitrous, I think. But there's a question that, is it a general rule of thumb that you will always, with the pure oxygen usage, you will always have less stripping and eventually less N2O emission? Is it like a general principle we can think of?
Giacomo, are you wanting to start?
Yeah, I can give the appetizer here. So we're busy also with one of these cases. It's very interesting because it actually reducing the stripping and maintaining the N2O in the liquid, you give a chance to consume it further, right? So you have the chance to remove it there. Once it's stripped, it's gone. So it can be a good strategy. However, the operation of the reactor and the mixing and the way the oxygen is injected then becomes critical to have optimal conditions, not to trigger AOBs to produce more, which is so it's a balance as usual.
So in fact, if we summarize that comparison a bit, probably it's then You have a mixing impact because pure oxygen is a way lower gas flow rate compared to an airflow rate. You have probably a transfer impact because the local transfer rate of oxygen is way higher. So this might impact the local DO and hence the local pathways and N2O production. And then third, you have the stripping. So yeah, it's quite a big deal, all these things combined.
Yeah, it just asks for more, I think, in-depth analysis in the combination. Yeah. Okay, so I'll maybe take another question. Is about so you spoke about the mitigation strategies. Is it a possibility to have ammonia buffer, for example, and then not let the ammonia completely come through directly, but instead in intermittent peaks of ammonia in a controlled way?
You mean
that be just
a buffer tank to shape the peaks?
Yeah.
Okay.
I don't know, Giacomo, have you seen that, these strategies on feeding?
Well, that's a possibility. Then the buffer tank has other issues in the management. So with anaerobic behaviors and storing how much you need space for that. So still it has an impact on the both operation, maintenance, and so on. But surely, shaving the peaks can help the dissolved oxygen controller, and the PID can be more relaxed instead of running behind the ammonia fluctuations. Conceptually it can work.
Yeah, this also makes me think to a case we had in the Netherlands, in Eindhoven with Waterschap de Dommel a while ago, where one of the questions was, how can we limit the impact of ammonia peaks on our wastewater treatments within our existing reactor? And then we started altering the mixing because there was one specific mixer pushing forward a specific flow, leading to less conversion, let's say. So we tried to make optimal use of that volume. So that was actually a project you have been working on closely, Usman, that one?
Okay, if you have some more time, I can squeeze in a couple of more questions.
Yeah.
There are questions about, of course, different technologies. Partially, you said something about that we are still investigating or we are further expanding into other technologies. But specific questions have come from multiple people about aerobic, granular aerobic technologies. What is our take on the possible N2O footprint of those technologies? Tricky one, I think.
Yeah, I will mute Usman. So it's you or Giacomo.
Yeah, it's tricky. I mean, as you saw, it depends on so many things. So it's very hard to just pass a judgment so quickly. I think some research have shown certainly some. I mean, both sides, and there are of course people who actually say it's causing even more, and some actually, So there's no consensus. Of course, it needs more, I think, time to mature such a technology. I mean, assessment. Compared to conventional, because in conventional system, you get a lot of opportunities to measure and you have a lot more data available. It's much more accessible, where these technologies, of course, just because they are not so common, it also has a little hurdle to get into the deep. Maybe Giacomo, you can add.
Yeah, well, I can add from my personal experience with granular technologies. I mean, the operation, it's very delicate there, and it's very important to maintain those tiny balances. Now the technology has reached a level of complexity and capabilities that it's becomes to be more and more interesting. With regards to N2O emissions, there are still wide there is no general consensus, I would say. That's what you observe, because I can imagine that the same technology also operated in different parts of the world or from different utilities can also generate very different emissions.
Yeah,
So
fundamentally,
it's surely, operation, it's the key, and it has a lot of potential, for sure.
Yeah, fundamentally, probably if you look at the biochemistry and the physics, let's throw some fancy words. Yeah, of course, what is very different with the conventional activated sludge process is the diffusion, I guess, right? And the residence time of these nutrients inside a granule or a biofilm. And yeah, of course, what happens at the interface then, and what happens within the biofilm, and what are the extreme conditions happening there? Yeah, that has I can imagine, for example, the biofilm thickness has a huge impact. So a lot of research is going on, and we are, of course, seeking ways on how to model those things in the most simple way as well, to help some of the acute questions. Yeah.
Okay. Thank you.
I want to thank everyone for the huge amount of questions here are popping up. I will not manage to answer all of them, but we will in the second stage.
What we can do is that we can maybe address some trends. So what I see is a lot of questions about in the pro towards pure oxygen use and also against it. So maybe I will just frame a question in a way that we are able to answer most of them. Of course, given the stripping factor, the chances are that we will not emit a lot of N2O. I think that's something we can all agree upon. But then what about the dissolved N2O, which might end up in the effluent and in the clarifiers? So because we are not measuring, it doesn't mean it doesn't exist, the N2O that is being produced. So what is our take on that? Maybe we can let Giacomo say something about it.
Yeah, I can start. So yeah, that's exiting the plant, that N2O, and it depends on the conditions of the receiving body. So if it's a river, a bigger river or a smaller one, and the dissolved oxygen that is present there, the biological activity, depending on that, the N2O can be further reduced. If there's no much dissolved oxygen, for instance, or close to the sediments, that can happen, or it can even be further stripped. So it is actually a full emission. So it depends on the receiving body, but yeah, it should be a concern in some cases.
So Giacomo, if I understand correctly, if you have significant N2O in your effluent being discharged, the only reason to get it removed is you need oxygen in a combination with carbon in the river.
Yeah. You need anoxic conditions to let heterotrophs eat it up. Yeah.
Or okay. Yeah. Exactly. Yeah.
Okay. Thank you. It's a long debate, to be honest. So we'll use another opportunity for that. But maybe another very relevant question is because if you look at the trends, of course, the N2O, greenhouse, climate change, that's one side of things. But on the other side, on the same time, we are also looking into intensification of our processes to use less space and to accommodate more and more process within the small space we have available. But can it be that these two processes, mitigation and intensification, can go hand in hand, or is it simply impossible?
Yeah, interesting question. Huh? That's quite fundamental.
Yes.
Yeah, there are lots of debates going on, and when we talk to a lot of utilities, there is so much going on. Also, the discussion on decentralized treatment versus centralized. So decentralized is typically small and modular. I can imagine if we just look at a reactor standpoint, a reactor design standpoint, that it's if you now have to design for completely from scratch a new decentralized system, that you have quite a clean slate to design for optimal effluent while designing also for minimal N2O. I can imagine working within very big existing infrastructure is a bit more difficult. But then, yeah, for the rest, and I don't know if there are other thoughts here. Feel free to use the chat also to contribute in the discussion on this, because yeah, it's quite a wide one.
Yeah. Okay. There's a question about, will we put the link of recorded session? I think we will send it through via email.
Correct. Every person that registered for this webinar will get the recording. Yeah. This week.
Okay, one question maybe, is there a possible way to measure the total N2O emissions? And I mean, the total, which means that it's also not, for example, if you talk about pure oxygen, we are only looking inside the bioreactor, but what about what happens before, how the oxygen is actually derived? So there is also a footprint linked to it. Of course, probably it's higher or lower than the compressed air we use normally in the bioreactors.
Yeah.
But that's example. But actually, the question is about larger other technologies. That
Mm.
is there a way to account for the whole list of things, kind of a life cycle assessment a bit on the carbon footprint?
Yeah,
And there's a
interesting
piece of
question.
a puzzle. Yeah.
Usman, yeah, if you look at the recording or you attended maybe the first webinar a few months back, we had a slide of juggling the three balls, which are effluent quality, operational costs or capital costs, so your costs. And now finally, we have a third ball, which is carbon footprint and N2O. So as a wastewater professional, you have to juggle these three. Yeah? They are conflicting all over the place. It's very complex. So we had a discussion with somebody today from a Dutch utility this morning, and she was saying, yeah, actually, operating wastewater today in 2022 is quite complex. If you compare it to, if just imagine you would just have to limit costs and achieve a effluent limit. So yeah, we have way more to account for. And what we believe is that models can account for these three very big categories: costs, performance, and carbon footprint. And if we then look into integrated modeling, which might become very important in the future, connecting plants, connecting different units, you can really make quite some decisions. But again, it will depend a bit on where you put the weights, probably. Where do you put the weights? Do you put the weight on your costs or on the carbon? Where do you put the weight of your decision criteria? Yeah, but I think models can be a very objective way of at least mapping the impact on these three.